Okay, so this is going to be part one of the R tutorial. There are going to be two parts. In part one, we will talk about generating a ROC curve, as well as compute the AUC to validate a logistic regression model. In part two, we'll talk about the multinomial logistic regression. So kind of makes sense to split this into two parts. So for the first part, we'll use this data set, the Titanic data set, which contains information regarding the survival of passengers on the Titanic, along with a number of variables such as the gender, age, and how much the passenger paid for the fare. So, as I say, in this first part, we're going to look at validating our logistic regression model. So, the way we do that is to split the data in two, right? One part being the training data set, right? And the training data set is the one that we use to build the model, and the other part will be the testing data set with which we use to validate the model, right? So training set used to build the model, and then we see how well that model performs on the testing set. So typically what we'll do is we will randomly split the data, right? So we'll just split the data randomly. Um, so that's the following code to type it in. So first things first, let me just read the data in. And you'll notice that when I read the data in over here, you notice that I didn't use the attach function, and I'll kind of mention that in a little bit why I didn't use that over here, but notice that I didn't use that. So to split the data is basically these lines of code, and I'll kind of go over what each of these lines represent. So the setSeed function is used to ensure that the same data points are sampled each time the code is run, so that when you see the results that I present and when you run the same code, you will get the same results, right? The reason is in this part where you do the random splitting, right? Each time, if you didn't use the setSeed function, right, you will get a different training test set split. So to get the same split each time that it's run, we have to set the seed. Now this sample.int function is used to perform the random splitting. So a few things to take note of in the code. The first one is basically the number of observations, so the number of rows in our data frame. This second argument represents the number of observations you want to sample. So the code I have written over here is going to be 0.5 times the number of rows, so half the observations. And I use the floor function here because if you have an odd number of observations, right, you can't sample half a data point. So the floor just rounds it down to the nearest whole number. And replace equals false means I'm going to replace sample without replacement. That means if a data point is sampled from my data frame, then it cannot be sampled again. So this line will actually generate a vector that is half the length of the data frame, and these data points in this sample will be in the training set, right? So, right, data equals basically I want the rows that correspond to the observations that I sampled here, and this minus sign for the test is basically the other data points that were not sampled. So if we just to take a look at, right, so let me just type sample, right, so samples, right, basically says it samples observation 507, 175, 699, so on and so forth, and this is basically a vector, right, that contains the observations that are going to be in the training set. So this is basically how we get the observations into the training set, and the minus sign means, right, those that are not these observations, those will go into the test set. So that's basically what we do over here, right? If you want to change the proportion in the training set, you can kind of change this proportion over here. So right, as I said, I use half the data points. So to fit a logistic regression model, right, so we're going to use the training set to fit the logistic regression model. So notice the way I wrote it over here. Notice, remember again, I didn't use the attach function. Response variable, predictors, family equals binomial for logistic. And here I put data equals train. So it's telling R that in this function, I only want to use the training data set. Right, so notice I didn't use the attach function. If you have multiple data sets, in this case, we do have multiple data frames, right? The training data frame, the test data frame. Do not use the attach function if you're working with multiple data sets. This is especially going to be an issue if your training and test data sets have the same variable names, which we do have over here. So don't use the attach function when you have multiple data sets. So this basically fits the logistic regression model. So let me just run all of that, right? So it's fitting the logistic regression model using only the training data set. So the next thing that we want to do is to validate how well our model performs on the test data set. So one of the tools that we can use is to produce an ROC curve. So we're going to use a number of functions that can be found in this ROCR package. So let's load it first. And these lines of code generate the numbers, the calculations that are involved in generating the ROC curve, and then this basically just produces the plot. So a few things to take note of. This line over here basically says, right, so result is where I have my training model, right, my model that's built on the training data set. So using that model, make predictions on the test data set, and type equals response means give me the estimated probability. So if you don't put type equals response, R will actually not return the probabilities. I believe it either returns either the log odds or the odds. So we have to put type equals response for the probabilities. So this preds basically calculates the predicted probabilities on the test data set. Now, the variable rates over here stores the numbers associated with the confusion matrix or the classification table. And this line over here basically kind of sets up the ROC curve where we say the axis I want the false positive rate, and the y-axis I want the true positive rate. So TPR for true positive rate, FPR for false positive rate. So that's kind of the standard, right, in ROC curve. True positive rate on y-axis, false positive rate on the x-axis. This code here, this line just produces the ROC curve, and this basically produces the diagonal line with which we compare our ROC curve with. So let me just run some of these lines over here. So let me just run these first two. Right, so as I say, preds will now store all the estimated probabilities of survival. Right, so for observation 707 in the test data set, that person, based on the model, has an 18.7% chance of survival. This line, as I said, produces the numbers associated with your classification table. This part over here basically stores the true positive and false positive rates as you vary your threshold. And this one just produces the ROC curve, right? And we always say, well, let's compare the ROC curve with the diagonal line, which represents a random guess, right? So if your curve is closer to the top left, then you perform better than the random guess, which, as I've kind of mentioned, isn't the highest of the best like yardstick to use, right? Okay, we're better than random guessing. Not a very high bar over there. The AUC, right, to calculate it, we can just use this function called performance to find the value, the area under the curve. So let's produce this, and this is basically the AUC, right? So 0.818 over here. One other thing that we could do is to create a confusion matrix, and right, if we want to use 0.5 as the cutoff value, then we can type this line over here to produce the confusion matrix. So the table basically produces a table. The first value that we're putting here represents what you want to put in the rows. So test $survive is basically the actual values for survive on the test data. So the rows will represent the true values. And this will basically be put in the columns, right? So the columns will represent what the model will predict based on a 0.5 as the cutoff value. So let's just produce this. Right, so that's the confusion matrix over here, right? So it's basically telling us the rows represent the true values of the test data set. So in our test data set, we had 210 people who did not survive. 180 of them had probabilities less than 0.5, so 180 of them were going to be classified as not surviving, and 30% of them will be classified as having survived. And this second row represents those who survive. So for those who truly survive, 44% of them, 44 of them were classified as not surviving, 100 of them were classified as surviving, right? So the false positive rate, right, is basically saying right? Out of all those who didn't survive, how many of them were wrongly classified as having survived? So it's going to be 30 over 210. So that's the false positive rate over here. I kind of pose a question, right? How should the cutoff be changed if we need to lower the false positive rate? So if you want to lower the false positive rate, right, you basically want to make it harder, right, for individuals to be classified as having survived. So you could actually just raise the threshold, right? So raising the threshold just means you're making it more difficult for someone to be classified as having survived, and right. So now the false positive rate is 9 over 210 over here. Okay, so this is basically how one produces the ROC curve and generates the confusion matrix to validate a logistic regression.